compression-free energy dissipative device. Alright. So when we talk about earthquake, we talk about lateral force that is attacking to the structure. Alright. This lateral force, we have many ways to design for the building to resist the earthquake. We can design the building to be very, very strong, okay, which might not be so economic, but good for economical point of view. We can put some other element which is so-called the damper or energy dissipative device. We can make the building a little bit softer, more flexible, but with the help from this device, we can keep the structure stands up after the earthquake. So many kinds of dissipative device available in the world. In Japan, we see a lot of base isolation system. Also, many places around the world, people use the brace that contributes to the horizontal resistance force of the building. For the brace system, we have many kinds of brace. All right, I'm gonna go through one by one. First of all, the conventional brace. Conventional brace is a brace that is designed to be always elastic. So this will increase the stiffness to the building. It makes the building stronger, stiffer, but at the same time, when the building is stiffer, you expect more force that will attack to your building. You might have problem to your foundation. So the foundation could be bigger, not quite good. We have the other system, which is so-called the fluid viscous damper. Right? So the damper will be put in the diagonal fashion like this in the building, right? And here inside the damper, you have something that is more or less like the hydraulics piston. Okay, so the energy dissipation will be through the viscous flow of the fluid, which is some sort of oil inside. Well, this system is quite good, okay, very, it is proven, but in some case, there is a report that when it is subjected to some sort of ambient vibration for a very long time, okay, there's a report about the wearing of the hydraulic, of the piston, and then that caused the leakage. So the replacement of the leaked piston is a pain. The next one is a system that you have seen already. That's a buckling restraint brace. So these metallic dampers use the hysteresis of steel under the reverse cyclic load. So you can see here, this is the steel core that is the part that helps dissipate the energy. But you know very well that when steel, which is quite slender, it is subjected to tension. Okay, you can dissipate energy through the tension yielding, right? But when you have the reverse load going on into the steel, that steel core will be subjected to compression, and what you expect will be the buckling of the steel core. So buckling restraint brace overcome this problem by putting the casing. The casing is nothing more than just a steel tube, and then you put the concrete or mortar inside. So that steel core will be confined under compression, so buckling will not be possible. And then the yielding can occur in both tension cycle and compression cycle. So this system will be able to dissipate energy and will be ductile enough. You can see that lately people develop from the constant cross-sectional area core into the reduced cross-section area, so the yielding will be confined over some area over here, and then around the connection they enlarge the cross-section, so no non-linearities or any stress concentration occurs in this area. And these are many kinds of ways to confine the steel core inside. So ranging from just traditional steel tube encased with the steel mortar packed inside, and there are many, right? You can see the literature. And these BRB are installed all over in the circumference of the building, maybe in the internal part of the building. And in the market nowadays, there are majorly three players for the for the BRB, all right? Unbonded brace is a trademark from Japan, so that is Nippon Steel Company. Cold brace and Star Seismic are from the US, so they are doing very good in this business. So these are three major suppliers of the brace, the BRB. So now the question comes up, actually this question comes up when I walked with Dr. Punchet to the canteen one day 4 years back. We talked on the walk, we talked about the BRB. And then I asked him, okay, what if I can make it compression free? So if it is compression free, then I don't need the casing, I don't need the restraint. He said, okay, you're welcome to do this, all right? If you can come up with a good mechanism to free the compression in the brace, then that might be the good thing, all right? So let's see, okay, what might not be so good about the BRB, or what might be the improvement from BRB. First of all, BRB, you might have some sort of bending going on in BRB because when you have the connection, which is the welded connection or maybe the series of bolt connection, it is not actually the pin connection. It can produce some bending moment. So the BRB is actually designed for axial action only, right? Yielding in the axial direction. But now you might have some bending action involved. Difficulties in installation. The BRB is generally made from the factory, so the precision of the installation is the key, right? For the brace like this, the tolerance could be as low as 0.8 millimeters. So that means the contractor must be a very, very good contractor, okay? Just very few millimeters error in fabrication may cause the problem to the contractor. And the last thing that is, I think, the key question about the BRB is that the unknown condition after the earthquake. So think about a multi-billion dollars building, all right? You have a high-rise building, 40, 50 stories. You put the BRB inside this building, all right? And then the building is undergoing a major earthquake, all right? But building is still standing up after the quakes, all right? The problem is, first question that the owner of the building will ask the engineer is that for how many times that this building will be able to resist the earthquake? How about the next quake? Will it survive or not? This is a key question, right? But we have no idea about what's going on in the BRB because it is simply just a steel encased in the concrete tube. So we don't know how much plastic strain is going on, how much more the system can withstand the earthquake. So I think this problem has to be addressed. This shows a relationship between the core strain versus number of cycles of force application. So you can see that the higher the percentage of the yielding you have in the core, you will have less number of cycles of force application. Replacement issue. You think about the BRB, we have a big steel core and you pack with the mortar inside, right? So the weight of each BRB will be quite heavy. And these BRB are installed all over the building, maybe just a very inner part of the building. Well, it is possible during the construction because you use the crane during the construction, but thinking about the complete building, all right? After the quake, this building is not accessible. The heavy equipment cannot get inside. This one is a parking garage, so okay, you might have some chance to put the heavy equipment, but think about the office building and you put the BRB inside. Or maybe for this case, the BRB is quite long, 7 meters long with this size, right? So in order to take this out, you need to remove this facade out. So that's a big work. So if we just eliminate the compression out of the equation. So if we don't have compression, we will not need the buckling restraint. That's the keyword that I will give you for today. So, how to remove the compression from the system? I would like to introduce you the device which is so-called the compression-free device, which is basically it's just a cam grip. You have the grip at these two locations. At the middle, it is a steel core. So whatever kind of low use strength steel can be used. Right? Steel core will be at the middle. If you look into this picture, you'll find that if I push the steel core upward, it will just freely slide through these two cams. But when I pull it down, this force will be balancing with the pulling force. So this will allow only one directional motions. It can be compressed freely, but under the tension cycle, it will engage the core and then the force will be resisted by the two cams. So the first one, which is a prototype, was put into the testing machine. We find that we apply the reverse cycle of motions. We find that it slides through for the compression very nicely, and for tension, force part, it engage the brace, the core very well. So we enlarge it to the more capacity. This one is 30 times. I just want to check if it is just a fluke or not. So okay, maybe put the bigger one into the test, and we find that for the small one and for the big one, they both work very well under tension, and it disengages the compression rapidly. Next, I put this energy dissipative device into the brace configuration. So you can see that this one is the compression-free brace. I didn't show you the inside of this brace, but basically the mechanism is exactly the same as just the device. So this is the brace, and this represents the column, this represents beam, and this is the hydraulic actuator, and the rest is just the reaction frame. So we will test the structure under the cyclic displacement motion. Here is a picture of the real test setup. We have the actuator here, we have displacement transducer to measure the story drift, right? And we have the transducer to measure the elongation of the brace. We have load cell, so we can produce some very nice graphic in a few slides later. We put this system through many load protocols. So we have the apply displacement load protocol, and we see how the system responds to the load. How the force and displacement relationship can be obtained from the CFD system. All right, so let's take a look at this one. We have the picture of the test on the left. This is the force in the vertical axis and drift, which is the interstory drift. Okay, relative displacement between this point to this point that define the drift. So you can see from this picture here that we have quite stable hysteresis loop. All right, so the loop is pretty much predictable, and you can see that the loop is quite nice and fat. What is the meaning of this nice and fat loop? It is a hysteresis, right? So the area enclosed in this loop between force and the displacement on the drift just implies that how much energy that the given system can dissipate the energy. Alright, I'll show you the next picture. This is a different load protocol. We have the constant displacement or constant drift applied to this system. So now you finish the first cycle, you see some of this part here which depicts the strain hardening. Right? And then repeats the second cycle, you can see that it is pretty much predictable. So I'm back there, and my student is pumping the hydraulic actuator over there on the scaffolding. We have plenty numbers of the tests on this energy dissipative device or energy dissipative brace, we find that all the tests give us very satisfactory result. Our hysteresis is very, very constant. And the beauty of this device is that after the earthquake, we just remove the core of the brace, which is the mild steel that we use to dissipate the energy. So we take it out, and then we throw away. We take the next one, push it in, put everything back into the original configuration. Then the building is ready for the next quake. So this is a beauty that those who are in the earthquake-prone area, those who suffer from earthquake like very often, may give a consideration on this new technology. This is a plot between core strain, which is the sacrificial steel, versus displacement. So horizontal axis is a displacement, and here is the strain. You can see that strain just keep going up. Strain that is positive denotes the tensile strain. So in the core, we have only just increasing strain all the time. You push forward, push back. You can see that when you push forward, you have the increasing strain. But when you push it backwards, strain stay constant. It stays constant because after the yielding, and we put it under the reverse, which is a compression cycle. The core, the device disengage the core, and it doesn't increase or make any change to the force, internal force in the brace. So you can see the flat behavior like this, and then when you push it forward, again it picks up the load and going back horizontally, and picks up and go back, and picks up and go back. So we have this kind of behavior for all the tests we run. This is another picture that this is the increasing drift. In the previous case, I think we have the constant drift test. Alright, stress-strain relationship on steel core. We also extract the information. We can make a stress which is interpreted from the load cell information, and strain from the strain gauge we install on the core. You can see something that you have seen from the strain of material course. This is exactly like a steel stress-strain relationship. You have the yielding and then strain hardening. So this behavior can be seen in the other specimen. It is quite stable. For this one, we put the specimen under the load protocol, and I think approximately about 60 cycles, but you can see lots of lines going on here, but at the end we can construct this stress-strain relationship. And this device has a potential to expand into other application, right? So as it is an energy dissipative device, it does not need to be only used in the brace configuration. We can make use of it in this system, which is a rocking wall system. You have seen the rocking wall system in the previous presentation already. But with that rocking wall, when you put the rocking wall along with the energy dissipative device, the building will be more resilient. So the device is installed here on these two sides. Where the wall is rocking, energy will be dissipated at these two locations. The other configuration, we try to make use of this device in the frame system. So we are trying to come up with a good setup or installation in the frame system. Alright, so in conclusion, this concrete energy dissipative device works very nicely. It engages the tension and disengage compression. We don't observe any problem about the locking of the cam. So the system is quite robust. For me, we try to put this under the real dynamic test, because this is very slow loading test. We might not see any problem as of now, but if we really put it under the dynamic situation, we may find some problem, but as of now, it is very robust. We also have some study, numerical analysis that make comparison between the CFD and the BRB, and we find that the CFD and the BRB system are quite comparable. So the performance of the building is more or less the same. After the earthquake, this used steel core can be just thrown away. We can have a spare part kept in the building. So just right after the quake, the maintenance people just grab the steel core, put the new one in, and then you might have the first hit, 7.5 magnitude. You might expect some aftershocks, maybe magnitude 5, right? So you can put the new one, and then you can make sure that the building will survive the next consecutive quakes. So this is the beauty of the system compared to the other system that you cannot replace the damaged energy dissipative device easily. This one is the selling point of the system. Large tolerance for installation is possible because the steel core is adjustable. So even the construction quality is not that good, but due to the nature of the system that it is adjustable. So the installation is not a problem, unlike the BRB. Alright, thank you, and